We've actually done quite a bit with induction, and I want to review some of the stuff we did just so that you can kind of put it all in context. The first kind of induction that we did works only on the natural numbers or the integers that are greater than or equal to k. Okay. In fact, the naturals are the integers that are greater than or equal to 0. Okay. And so the induction hypothesis is going to look like this. It's true for n, then we need to prove that it's true for n plus 1, right? So we assume that the theorem holds for n, which is fixed, okay? And then we have to prove that it necessarily follows for the next integer, which is n plus 1. This is called mathematical induction, okay? And I didn't mention it, but the base case is going to be when k is equal to 0. Or, I'm sorry, when for the natural numbers is when n is equal to 0. Or in the case of the integers greater or equal to k, then the base case is when n is equal to k, okay? Now, we also have kind of an alternative way of doing this, and that is when we have the same setup, something for the naturals, so for all the integers greater or equal to k, we can actually say that it's true for n minus 1 and then prove that it's true for n, okay? That's equivalent, right? That's not really a new kind of thing. It's just something that's sometimes convenient. And I actually prefer to do it this way, simply because the thing that I'm trying to prove, right, is just the property of n, which is what I start with, right? So I may want to prove that 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2, right? And so in the induction step, what am I actually trying to conclude? Oh, that 1 plus 2 up to n is equal to n times n plus 1 over 2. That's the theorem that I started with, right? So to me, that feels more natural, to assume that it's true for a smaller n and then show that it's true for n, okay? But it makes not a single bit of difference, right? You can do it either way. Okay. All right, now here's something else. And again, it's the same setup. It's some property that's true of the natural numbers or of all the integers greater or equal to k. And what we'll do is we'll assume that the property holds for all k that are less than n, and then try to prove it for n, right? So the basis is the same, n equals 0 or n equal k. But then what we'll do is we'll say, in order to prove this, let's assume that the theorem is true for all k less than n. So not only can we use the fact that it holds for n minus 1, we can also use the fact that it holds for n minus 2 and n minus 3 and n minus 4 all the way down, okay? And a good example of needing that is, for example, when we're proving stuff about the Fibonacci sequence, right? Because the Fibonacci sequence depends not just on the Fibonacci number n minus 1, but on the n minus 1 and the n minus 2 number, right? So we might actually need properties for both of those, right? Not just for n minus 1. And that's why this is a very convenient form of induction. We call it complete induction. Some people call it strong induction, right? It's the same, right? That's just a form of induction. Okay, now what we did a lot in this unit, or in this section of this unit, I should say, is talking about inductively defined sets. And right now we only have one example of that, and that's lists, right? But in the next module, or actually in a future module, we're going to talk about trees, right? And trees are actually inductively defined types, and that makes sense. Like a binary tree, it's got a root and then a left branch and a right branch, and both branches are actually subtrees. Okay, so when you have an inductively defined set, one way of doing the proofs is called structural induction, and that's what we did in those last two examples. And you simply assume that the theorem holds for a subpart, right? So if we're talking about lists, then it holds for the remainder of the list, okay? And then we have to prove that it actually must be true of the entire list, okay? So that's the induction step, right? It holds for a smaller list, then it also holds if we take that list and we add an element in front of it, okay? So that's what we did, okay? Now, you can also kind of do an equivalent of strong induction. And what we're going to say is, well, not only does it work for the list after I remove the first element, but it actually works for any of the lists that is made up. So if I have the list 1, 2, 3, 4, 5, then I can assume not only that it works for 2, 3, 4, 5, but also about 3, 4, 5, 4, 5, 5, and nil, right? So that's kind of equivalent to the complete or strong induction. This is actually called Noetheric induction after Noether, who was an absolutely fantastic mathematician. And she does not get enough credit for the work that she did, but she's one of the great mathematicians of all time. Okay, now I'm going to make this even stronger. Okay, so instead of talking about an inductively defined set, why don't we talk about a well-ordered set, any well-ordered set? Okay, so in here, there's kind of a simple induction you can do. Let's just assume that it holds for all smaller elements. Now, I can't just assume that it holds for the immediately smaller element like we do for example, the natural numbers, because there's not necessarily a notion of the immediately preceding smaller element, right? See, the natural numbers are not just well-ordered, it's a chain. Right, is 1, 2, 3, 4, 5. So if I'm at 4, I can go up to 5. I can go down to 3. That way I can do the n plus 1 or n minus 1 induction, right? But no matter where I am, there's always a well-defined next or previous. But that's not true in a well-ordered set in general, right? I could have a well-ordered set, like for example, subsets of some large set ordered by set inclusion, okay? And then there isn't a next biggest or next smallest, right? If I have a set with 4 elements, I can take any one of those and I have an immediately smaller set. I wouldn't know which one it is. So instead what we do is we just assume that it holds for all smaller elements and then just keep walking down, right? That's actually what noetheric induction is. So when I said true for all smaller lists in an inductively defined set, I'm actually using noetheric induction, right? It's just that I'm using this style of induction on an inductive set. And inductively defined sets are always well ordered by subpart. Okay, so if you take a tree and you keep walking down the tree, then you're eventually going to get down to a leaf. That's what well ordering means, right? No infinite descending chains. If you have an infinite tree, well, all bets are off. And that's why all of the proofs we do are about finite trees. Okay. So that's it. Okay, those are all the different forms of induction that we've covered and that we will cover in this class, and keep them straight. We have mathematical induction, we have complete induction, we have structural induction, and I just want you to be aware of noetheric induction.